All right, so we're going to talk about Lewis structures. They're named for a very famous American physical chemist, Gilbert Newton Lewis, who, among many other things, developed this convenient way to write the structures of things. So we take the valence electrons, which will be the same as the group number, and that will be the number of dots that we use to represent the number of electrons around an atom. So hydrogen, for example, 1 dot. Carbon, 4 dots. Oxygen, 6 dots. Chlorine, 7, right? All right, so a complete set of electrons in a given n level translates as high stability. That is, all the electron levels that can be filled are filled. And on the periodic table, this would correspond to the far right-hand column that we call the noble gases, and they're so called because they don't react with very much. So if you have a set of filled s and p levels, you have 8 electrons, and this tends to be called the octet rule. That is, and I'm putting this in quotes, all atoms want 8 electrons in their valence. But the truth is, this really only holds for a small part of the periodic table. It's not much of a rule. It's really no good after period 3 because it turns out many heavy atoms can have many more than 8 electrons in their valence. And there are some light things that are perfectly content with fewer than 8 also. But it's a pretty reasonable guiding principle when you're drawing a structure in terms of knowing where to distribute the electrons and how many bonds things can have. Okay, so if you go from a Lewis sort of dot picture and translate that into typical patterns in bonding, you'll see that it makes perfect sense. So the number of bonds that something typically forms is related to the valence and how many electrons it needs to complete an octet. So hydrogen, you put a dot there, it'll make 1 bond. It needs 1 more electron to make a bond. Beryllium, 2 electrons, it can make 2 bonds, right? For a total of 4, which is obviously less than the octet. Boron, I'm showing you these oddball light ones that sort of violate the octet. Carbon, 4 bonds. But those 4 bonds can be arranged in these different ways. We can have 2 single bonds and a double, we can have 2 doubles, we can even have 1 triple and a single. But it's always the same valence every time you do that. Nitrogen, typically 3 bonds and 1 pair of electrons, typically referred to as a lone pair. And again, it can also make double bonds, and sometimes you'll even see it like this, ionized with 4 bonds on it. If we look at oxygen, again in group 6, typically 2 bonds. 2 single bonds, a double bond, or maybe even 1 single bond with an extra charge on it. Those are typical patterns in bonding, all based on the number of electrons that something has as its valence and how many it needs to complete an octet. So some guidelines for drawing Lewis structures. I'm going to number these, and we'll use the example of water in doing this. So first of all, you're given a formula, and from the formula you want to arrange the atoms in a sensible way. Sensible meaning you're not doing something ridiculous by trying to put hydrogen in between 2 things, or just putting everything in a straight line. So a good rule of thumb, unique atoms, put them in the center. Things that can only make 1 bond, they're going to have to be on the outer edge. They can't be in between 2 things, right? And things that are more electronegative than others, those typically are on the outside edge too, or on the outer circle. I mean, it's really a simple guiding principle, but it works almost all the time. Put the more electronegative things on the outer edge. Put the unique atom in the middle. So if you have H2O, do this. Put the oxygen in the middle, hydrogen's on the edges. Do not do that. It's ridiculous. You can't make a compound out of that. Okay. So take a look at how many valence electrons we have to play with here. We get the total number, and then we're going to distribute them. So add up all the valence electrons. So for H2O, I have 2 hydrogens, so 2 times 1, and then I have 6 from the oxygen for a total of 8 valence electrons. Those 8 electrons are now going to be distributed in the form of bonds or perhaps non-bonding pairs. So, connect the atoms with lines. They're going to be in a compound. There's going to be something connecting them. Connect them with lines first. A line is a bond. A bond represents 2 electrons, 2 shared electrons. So based on our pattern, there's 2 lines, right? Now, we've accounted for 4 electrons by doing that. We still have 4 more to account for. So, using dots, we're going to complete the octet. Now, we're going to complete the octet on the outer atoms first, and then complete it on the inner ones, or inner one. Now, in the case of water, hydrogen is content with 2 electrons. We don't have to complete an octet on that. It's already all set. Now, I said complete the octet on the outer atoms first, or the most electronegative first, but those usually are the same if you've arranged it correctly. So there's 4 accounted for, right? Hydrogen's already content with 2, but we need to take care of the other ones on oxygen. So we're going to complete the octet on the inner one if necessary, on the inner atoms, making sure that all the electrons are accounted for. So again, the 2 lines account for 4. We're going to need a little bit more in the form of dots. There we go. 1, 2, 3, 4, right? Count them all up. There's 8 electrons accounted for. And that's a very simple structure. We've accounted for all of those things. We've done all the steps already. But just to be thorough, if you have to, make multiple bonds in order to complete the octet. So follow all those other steps, and then if you still don't have octets present on inner atoms, then rearrange some electrons so that you do by making multiple bonds. And then finally, I'm going to check what's called the formal charge, which is sort of an artificial kind of concept that treats all the atoms as if they were ions, in order to make sure that there aren't too many things or too few things attached to a given atom. Even if the octet is right, there may be a way to minimize it. So the formal charge is going to be the valence electrons minus the number of, I'm going to say number of lines, minus the lines, minus the dots. So minus the number of bonds, minus the number of electrons attached to it will give you what's called a formal charge. And that can be positive or negative or 0. And again, based on the electronegativity of the atom, it may be sort of more comfortable with one of those values than another one. So ammonia, NH3, we put the unique atom nitrogen in the middle. Hydrogens have to be on the periphery. We'll add up the valence electrons. We have 8 total valence electrons. We're going to draw lines connecting things to stand for bonds. Each one stands for 2 electrons. I'm combining steps 4 and 5 here. We're going to use dots to complete the octet. There we go. And we'll just take a look at steps 6 and 7. So 6 is not necessary, no need for multiple bonds here. And 7, the formal charge, well, hydrogen, that's okay. 1 minus 1 is 0. And for nitrogen, it starts out with 5, minus 3 lines, minus 2 dots is equal to 0. That's good too. All right, let's do another one. Carbon dioxide. We'll put the carbon in the middle. The oxygens are electronegative, they're on the outer edge. We've got 2 times 6 for oxygen and 4 for the carbon for a total of 16 valence electrons. Step 3, we're going to connect them with lines. Step 4, we're going to use dots to complete the octet on the oxygens first. Now you can see that the oxygen is all set for electrons, but the carbon is not. Okay? Now we've accounted for all 16 there, so we can't add any more. But the carbon is still deficient in electrons. So now we're going to have to rearrange some things. So we're going to take a couple of electrons and move them in to the center to stand for multiple bonds here. So we're just rearranging what we already have. We make multiple bonds to the carbon, same total number of electrons, but now the octet is complete on all atoms. So formal charge, oxygen 6 minus 6 is 0, and on the carbon 4 minus 4 is 0. We're all set. All right, another example. Carbonate ion, CO3 2 minus. I'm just going to go ahead and skip numbering the steps here. I'm just going to write the pattern down, count up the valence electrons, and I'm including the 2 additional electrons that make it an ion for a total of 24 electrons. We'll draw the bonds, complete the octet on the oxygens first, and that accounts for all 24 electrons. But the carbon still is deficient in electrons. It's got 6 electrons on it now. But if I take 2 from one of the oxygens and share them between the carbon and oxygen, now everybody is content with an octet. And the way that you represent the structure of an ion is to put brackets around it and indicate the charge in the upper right-hand side as a superscript. So we'll look at the formal charge on things. Now there's 2 different forms of oxygen here. That one, the single bonded oxygen, 6 minus 1 minus 6 is minus 1, which is perfectly okay for oxygen. Then the double bonded oxygen, 6 minus 2 minus 4 equals 0, which is good. And for the carbon, that's also 0. So it's perfectly okay to have oxygen with 2 different formal charges there. So let's take a look at the example of the phosphate ion, PO4 3 minus. Again, phosphorus is the unique atom. We'll put it in the middle, adding up the valences, 4 times 6, 5 from the phosphorus, 3 to make it an ion for a total of 32. Lines and dots to complete the octet, completing the octets on the oxygen. That accounts for all 32. So now let's check the formal charges, because everything has an octet here, but let's take a look at formal charges. So one of the things about elements like phosphorus and heavier things like that is that they can violate the octet rule. So here's the thing. Phosphorus is +1. The oxygens are all -1. We can make a double bond and make 2 of them into formal charges 0, which is probably a more likely structure. So total charge of 3 minus on that. We'll take a look at another example, this time of an organic compound. 2 carbons, 2 hydrogens, 2 chlorines, dichloroethylene. So carbons are likely to be in the middle, and they're likely to be connected to one another. The other guiding principle, now look at this, don't arrange them in a line. People tend to do that all the time. It's ridiculous and wrong. Don't do it. Hydrogens and chlorines typically can only make 1 bond. Again, there's situations where chlorine can make multiple bonds, but this is a very sensible arrangement here. So I'm completing the octets on the chlorines after connecting them with lines. Then I have these 2 other electrons left over, and I'm putting them on the carbons. So the way to deal with those odd electrons is have the carbons share them to make a bond. So the carbons are double bonded. So we can have 2 chlorines on one carbon, 2 hydrogens on the other one. Now, another way to do this would be to have a chlorine and hydrogen on each carbon, and that's also a perfectly legitimate structure for this. And there's yet another way to do it, which would be chlorines on opposite, I had them on opposite sides of the carbons. Now I can put them on the same side of the carbon. All of these are 3 different possible structures for this molecule. They're all correct, and they are called structural isomers.